Back in grade 11, you learned about electromagnetism. So this is a concept of a magnet with a wire. So remember, when you have a magnet and a wire, actually the wire which is actually coiled, that means when a magnet is brought close to a metal wire and in relative motion, some electric current will actually be induced inside this wire. So as you can see here, as I bring my magnet closer to this coiled wire, I can see that my light bulb is going to light up. So this means that I can actually form some form of electricity, and I can have some circuit running using this system. So this is called a induction of electric current using magnet. This is the concept of Faraday laws. So I'm not going to go much into details on Faraday's laws, but this is the idea that you have to have in mind when we talk about grade 12 topic, which is electrodynamics. Today we are going to look at electrodynamics. So this is one of the concepts that sometimes it's difficult or challenging, not really difficult, but it's at least a little bit tricky to understand. But we're just gonna talk about how we can use the magnet induction or the concept I demonstrated at the beginning to actually create some electrical machines. So that means we can actually use that system to have some different machines that we can use in our daily lives. So here we will talk about a generator and a motor. So we have these two machines, and we have to see that how we can use these machines and how they actually work. So a generator is basically some system which actually converts mechanical energy into electrical energy. So you might actually have heard about generators in your everyday lives, which actually are used to create some form of electricity. Remember, as we are here in load shedding, we are always familiar with the fact that we're gonna turn to generators in order for us to create some sort of electricity, in order for us to continue having some power. So here, this is where the generator actually comes into play. So in motor, a motor does the opposite. So a motor actually converts electrical energy into what? Into mechanical energy. So here that means if I can give you an example of something like a hair dryer, you will see that there's a little fan at the back. So that is a motor which is turning there. So when you're actually using your hair dryer, you're actually turning that electrical energy into mechanical energy. So that is one of the examples of a motor. So I'm gonna draw some diagrams here in order for you to see how actually these two machines look like. So here you can see that I draw some diagrams. So that means this is how this machine basically look like, but you won't see this in everyday life because it's just the system which actually controls how the system works. So here you can see that you have your magnets, two magnets, the other one is north and the other one is south pole. So here these blue lines will actually indicate magnetic fields. The same thing applies on the motor as well. So these two machines, they work in a similar way, The only difference is the energy conversion, but the system of how they work is basically the same. So here you can see that this is a loop of a wire here, so that means it's a loop of a wire. So in order for you to see what the difference between a generator and a motor is, the circuit at the end. So here this is the same for all these two machines, but when we get to the end here, at the end of this two machines, for generator you will have something like a voltmeter. So like I said, since the generator generates some electricity, so that means we will have to read the voltage which is created here on the voltmeter. Whereas in the motor, since we are generating mechanical energy, so that means we will actually connect the circuit with a battery. So we will have some source of power here, and then this power is the one which will make this loop to actually rotate. So the force will be created inside here between these magnetic fields in order for us to have some mechanical energy. This wire here will actually rotate because of the fact that we have a battery here. So this battery will supply the wire through inside here, so that we can actually have current moving through this wire here. So this is a coiled wire, the same as the generator. This is a coiled wire, and then here this is some rings. So these are some rings, and we have different types of rings, so we're going to talk more about them as we proceed. So these are some form of rings, and here these little boxes here are just something called carbon brushes. So now let's talk about a generator. So how does the generator works? So remember when I illustrated Faraday's law, generator works using that same principle. So it means that generator uses the principle of electromagnetic induction in order for it to work. So that means generator uses electromagnetic induction principle. Okay, my spelling there is not coming out well, but that is principle. Okay, so what is magnetic induction principle? Already when you know Faraday law, you will know that a current which is produced due to what? Due to a change in a magnetic field. Magnetic field. So if I go back to the drawing here, I can actually see that I have some magnetic field running across this loop of a wire. So that means this is magnetic fields. So that means as the magnetic field are actually running across this loop of a wire, that means that is when we can actually have electric current that will actually be formed. So anyway, as a result, this wire should actually rotate. So as this wire rotates, then electric current will actually move along this loop of a wire, and it will actually come here, and actually we can have a final reading on this voltmeter here. Pause my number. So now let's talk about the motor. How does the motor now works? Okay, so remember the same setting we have on generator is the same setting we have on a motor as well, but the difference is that with the motor we have a battery that will actually provide the wire with a electric current. So motor works using something called motor effect. So what is a motor effect? A motor effect actually is when you have a current carrying wire, so a wire carrying a current creates a magnetic field, okay, so you remember when we have a wire, just a normal wire which has a current running through it, we basically have a magnetic field produced around this wire. So as the electric current is running through this wire, magnetic field are actually generated around the wire. So hence when we have a wire which is carrying a current, the magnetic field will be created. So as a result, this magnetic field will actually like interact with another magnetic field. So another magnetic field is the one that we have on our system. Magnetic field causing what? Causing a force which pushes, or which actually, yeah, it pushes a wire to rotate. So that is actually motor effect. A wire which actually has a current has a magnetic field. So that means when we actually provide this magnetic, or this actually like this loop of a wire with a current, some electric field will be formed around here, and this electric not electric field, but this magnetic field will actually interact with this magnetic field which are produced by these two magnets, which will actually cause this loop to rotate. That is why we have mechanical energy. So we are creating a force that will create this, that will make this loop to actually rotate. So a force is created. When we talk about motor effect, it means that we have to produce some force on this loop of a wire. Okay, now we're going to talk about components and functions of both motors and generator. So like I said, since they have the same setup, then it's actually fair to generalize those components under the same heading. So that means we have the same setup or components in both motor and generator, but we will just have a difference of that. In a motor, instead of having a battery, instead of having a voltmeter, we have what? A battery. So one, we have magnets. And what do magnets do? They actually produce magnetic fields. Okay, so second component is actually an armature. So an armature is just a loop of a wire. So what does this do? It allows EMF or current to move through, to move through. So that means armature just allows the current to move through it. That's the simple function of an armature. So you can call it an armature or a loop of a wire. It's actually the same thing. So I'm just saying, in the case that you see the word armature and you actually get lost, it's just a loop of a wire. And then the third component is carbon brushes. So carbon brushes are those little boxes that are just outside of the rings. So if I go back to my diagram, that means we talk about these guys here. So those are the carbon rings. They are touching themselves with the external circuit and the rings. So basically, then if we talk about their function, it means that they maintain electrical contact with the rings. So I'm just going to generalize the statement. I mean, like, with the rings and external circuit. External circuit, let me put it like that. External circuit. Okay, so the we can actually have something like for like a motor, maybe in addition we have a battery, and then for a generator we can have something like just a voltmeter reading. You can have a light bulb, or anything like that. So those are just some components when we actually go further into differentiating between a motor and a generator. But the first three, they are available in both motor and generator. So remember, magnets, always those are the fundamental components to produce magnetic field. So we need magnetic field in order for our system to work. And then an armature, which is a loop of a wire. So this is a name for calling this loop of a wire. And we have carbon brushes. So sometimes they can just say brushes, but they are basically carbon brushes. So these guys, they are the ones which actually maintain the electrical contact with the rings and external circuit. Okay, so we have types of motors and generator. Okay, so this is called DC and AC. So it applies for both motor and generator. So what are these two types of operations? So we can call them, I don't know if it's just this is actually like when you say DC and AC, we mean how the current is actually moved around these systems. So with DC we have something that is called direct current, and AC is actually called alternating current. So DC current or direct current uses a split rings to connect the conductor to the external circuit. And here that means when we talk about those rings that I actually indicated at the beginning, it means that I actually just called them rings. Let me go back. I just actually called this just rings. So that means we actually going to actually differentiate these rings according to whether the system is going to be a DC or alternating. So that means instead of just having a ring, we're going to have a specific ring, and I have to actually redraw this in order for you to see, but I don't have to actually redraw the whole system, but I'm just going to show you how does the split ring looks like. So let me go back and actually indicate it. So a split ring, it means that you just have like a one ring which is split in half. So that means if I can actually draw that, so it's a ring split in half. So this is some 2D drawing. Doesn't look nice, but yeah, something like that. So here you will have your carbon brushes and attached on either side of these rings, and then there you have an external circuit. So DC actually direct the current in one direction. So the current in the external circuit is just in one direction. It doesn't change, it actually goes in one direction. But if we talk about alternating current, so that means we will have to have component such as slip rings. So this one uses a slip rings to connect to connect the conductor, is to connect the conductor to the external external, okay, this is not the right way of writing external, but external circuit. So that means I will actually have, it's actually like two split rings. That means is two rings which are not cut in half. So I will have one ring and I will also have another ring. So if I just draw this in 3D kinda, it will look like this. So I will have a carbon brush attached on the other side. So you have one carbon brush per ring. So one ring will get another carbon brush, and another ring will also get another carbon brush. So then you will have the external circuit. And then here you can connect either a battery or a voltmeter or anything that you actually gonna have, depending on whether it's a it's a motor or a generator. So this is just a wire that will go and become a loop on the externals, on the not on the external but inside or between the magnets. So this wire just goes to make some form of a loop between the two magnets. But the main component for direct current is the split ring, and the main component for alternating current is slip rings. So these two, they are the ones which actually will differentiate between a DC or an AC system, which is the same for both motor and generator. So whether you have a motor, if it's a direct current motor, it will have this component, and if it's a AC motor, then it will have this component. The same will apply for the generator as well. So if you have a DC generator, you will see by the split ring, and if you have a AC generator, then you will have a slip rings. So you will have two rings which are not cut in half. But a DC, this uses one ring which is cut in half. So here, let me complete the circuit and put this I'm gonna also put the voltmeter here as well. So this is my external circuit. So once you move out of the magnet field loop and then you come here through these rings, you are actually going to the external circuit. So this is the external circuit. So those are the two types of systems for the motor or a generator. So you have a direct current, which means that the current that is moving here is going to be in one direction, and you will be able to see this with a graph. And then for alternating current here, that means the current that is moving through the system is changing. It changes with every half turn of the coil. So unfortunately, I can't have something like a demo which actually can show you how this rotation actually looks like. It will be much easier if you can actually see the rotations of these loops when we talk about the change of the direction of the current. So alternating current means that the current that is being created, or which is yes, the current that is actually running through the system is changing direction, and we will also see how this actually can be shown or demonstrated using a graph. Okay, before I can actually move into graphs, let's actually try to put the functions of these rings in order for you to actually have a clear understanding of how are they different and what are actually their functions. So slip rings actually allows current to change direction every half turn of rotation of an armature or a loop. Okay, so and then here I'll actually talk the one that is different from the slip rings. Remember, split rings allows induced EMF, not EMF, but just induced current. Let me just put current because I've also used current here. Induced current to flow in one direction. So then these are the actually distinct difference between these two rings. The other ring actually allows the current to change direction. So that means as the loop is rotating, the direction of the current will change every half turn of a rotation. Like I said, I wish there was some demo in order for you to see how this movement of the loop actually can actually change direction, or show that the current is actually changing direction in every half turn of the rotation. But anyway, if you can actually try to find that information, it will be easier for you to understand. And then split rings allows the current which is induced, even here the same, the current is induced to flow in one direction. So that means the current is not going to change direction when we have split rings. But the common functions of these rings is just to allow continuous, the spelling of continuous, guys, continuous contact with carbon brushes, and the same one applies here. So even here the same will actually do the same thing with split rings. So it also allows continuous okay. So remember, I've been talking about graphs and graphs and graphs. Okay, so now we can actually have some graphs to show and differentiate between a DC and AC current. So for DC, your current will, or the graph will actually look like this. So you will have a graph which have a vertical axis and a horizontal axis. So here you will have rotations, and then here you're gonna have your V. So that is induced EMF. Yes, so here you're gonna have your V max, and then you're gonna have your V minimum. So that is the minimum when you go to the bottom. But for DC, since we said that the direct current does not change the direction, so what happens is that the graph will actually look like this. So it will actually look like this. Okay, you will have a starting point wherein the loop will actually be in some form of a position between the magnets. So here I can actually say that the position will be vertical, and when the position is vertical, let me try and have that in some drawings. So I'm gonna have my two magnets, and the loop will be vertical. So that means it's gonna look like this. It's gonna look like this. So I'm gonna just say that this is a vertical position of the loop, and then you have the magnetic field through this wire. So what you can see is that vertical position, you don't have an induced EMF when the wire is in this position, but when the wire is actually like in a horizontal position, so I'm actually gonna label this as a, so the wire is actually in this position, this magnet is too thick. Okay, so gonna be like this. So then you have the magnetic field through here. So then when the position of the wire is actually parallel with the, is it parallel? Let's say the horizontal position, yes, then that means the induced EMF will be at the maximum at this position. It's maximum. So I'm just gonna label this as some formula like A and B. Position A here, and then position B here, and then so since this is a rotation, so let's say this is like a clockwise rotation, so it's gonna rotate vertical, and then it becomes horizontal, and then it will go back to vertical again. So when it goes back to vertical, it's gonna be in a, again we're gonna go back to A, but remember the sides of the wire will be in a different position as a result. So here I'm just indicating that the position is vertical, and when we come here to B, then at the top maximum, then the position is horizontal. So I'm gonna actually indicate that as in vertical position, and then here you're gonna have horizontal position. So in order for you to actually see that the position of the wire across the magnetic field will actually determine the induced EMF in a DC current. So like I said, that is why the DC current, we say the direct current, there's no change in direction. You actually start from 0, you go to maximum, go back to 0, and then you go back to maximum, you go back to 0, and then you're gonna continue and continue and continue. So from here to here there's a half rotation, so that means vertical, horizontal, and then you go to vertical, and then horizontal, and then vertical again. So this is just a one rotation. From here to here is one rotation, one full rotation. So I like I said, I wish there was some form of a way to actually demonstrate this, but I hope it actually gonna make sense in some way. And that is how the graphs of the DC current or direct current looks like. And then let's actually go to the alternating current graph. So alternating current, let's say AC here. So again, you're gonna have a vertical axis and a horizontal axis. So here you have a rotation on the axis X, or horizontal axis, and then here you'll have the V, which is induced EMF V. So you're gonna have Vmax at the top, and then you're gonna have negative minimum at the bottom. Okay, so now since alternating current changes direction, that means we're gonna have something like a graph which will look like this. The graph will look like this for alternating current. So that means sometimes maybe in your exams they might give you a graph, and they want you to actually state whether the graph is for AC or a DC. So this is how you can actually know that. So like I said, here it's a start, and then you will have a maximum voltage, and then you will have a 0, then you have a minimum voltage, then you go back to 0. So again, if you start with a vertical position, so I'm gonna actually repeat the same pattern here. I'm gonna draw those small illustration of the position of the magnet. Okay, so here are the demos for the positions of the loop across the magnetic field. So like here at the start, you will have 0 induced EMF when the position of the loop is vertical. So that means that is where you can have A here, and then at the maximum, then that means the position of the loop is at horizontal, then that is when you will have B. The same thing will happen, it will go back to vertical again, and then you go back to A, position A, and then you will actually go back to B, but this B will now become a minimum. So as a result, this is how the alternating graph will actually look like. But remember, so since we are actually talking about the movement of the loop, it will actually be in different positions. So if I have a side AB here, and then I'm going to have a side AB, but it's gonna rotate. So as it rotates, then that means you will have this side moving into different directions. So that means it's not like I go here then go back, go here, go back. So it's a rotation. So it's a rotation. So that means each and every side will be exposed to a different position. So maybe side AB is vertical, and then the same side AB is actually horizontal, and then it goes back to vertical, and then it goes back to horizontal, but it will be producing a minimum voltage because of the fact that this is an alternating graph. So like, I hope this will actually make sense as well, but if it doesn't, just know that this type of a graph is for alternating current for both motor and a generator. So depending on whether you are given a generator or a motor, and then they have a graph which looks like this, and they ask you to actually determine what type of a graph is this, then just know that this is an alternating wave. So now that we actually tried to describe the movement or the rotation of the loop using graphs, we actually can use the rules to actually explain or to actually find the direction of some of the concept inside these machines. So that means these rules, some of them you actually, not some of them, but you actually did them in the previous grades. For a motor, we actually know that we have to use Fleming's right hand, not right hand, that was a mistake, left hand rule. So this rule, it predicts the direction of the force, or actually the direction of the movement of the coil. Okay, so that means if you are given a motor, the rule that you will use in order for you to predict the direction of the movement of the coil, or let's say a force, it's gonna be a Fleming's left hand rule. So then that means you can actually predict that, but not only necessarily to predict the direction of the force, you can actually also predict the direction of the current as well. So you can actually use it to predict the direction of the current, which is the induced current. Okay, so it doesn't only focus on the direction of the force or movement of the coil, but it can also focus on the direction of the current as well. So in a generator, we also have a rule that we can use. So this rule is Fleming's right hand rule. So Fleming's right hand rule. So this rule also can be used to predict the direction of induced current in the coil. But we can also use it to actually predict the direction of the force. But this one, it doesn't really much apply on the generator, because a generator, we actually produce electricity, so we won't really have to worry about the direction of the force of the coil, because like, since we're actually just producing electricity, we can basically focus the most in the direction of the induced current in the coil, but we can at least try and also predict the direction of the force, because we also have a lobe which is moving in some direction. So if we can know the direction of the current, maybe we can actually predict the direction of the force or the movement of the coil. So like the force can literally be the same as the movement of the coil. So then as a result, if we use this specific rule for a specific machine like motor or a generator, then just pay attention to whether you have a motor, and if you have a motor, then it's a left-hand rule, and if you have a generator, then it's a right-hand rule. So let's talk about those rules. So remember, in those hand rules, you will have a thumb, index finger, and you will have a middle finger. They have to be at right angle with each other. So you can actually see this type of a drawing in your textbook if you do, and you can see how they position these fingers. So the thumb actually will be measuring it, or it predicts, it actually predicts the direction of the force. So I'm gonna just say force or movement of a coil. Okay, index finger shows the direction of magnetic field, which is B. So here for the force I'll put letter F, and then for the middle finger we're gonna see the direction of the current. So current is capital letter I. So that means if we put these three fingers with right angle to each other, we can actually see the direction of the force, magnetic field, and the current. So depending on whether you have a motor or a generator, remember that for motor it's a left hand rule, and for generator it's a right hand rule. So unfortunately I just can't demonstrate these rules because it's more practical, and since I'm just doing this lesson behind the screen, I can't actually put my hand in order for you to see how to use these directions. So they will actually give a direction of either a force or a current. The direction of the magnetic field, it's always given. You won't really have to predict it, because as if you know the position of the north and south poles of the magnets, then you can easily see that you will have a certain direction for the magnetic field. So, and remember, for magnetic field, the magnetic field moves from the north side of the magnet to the south side of the magnet. So these are the rules that you actually can be using whenever you are working with a motor and a generator. So in our next sessions, we're gonna look at the calculations in this topic. So we were actually looking at the theory part of this topic, electrodynamics, and on the next sessions, that is when we're gonna actually look at the questions or calculations, because we also have some calculations here, and there are some formulas that you have to actually get to know how to use them and to play around with them.